Okay, well, welcome everyone to another seminar. This week we've got Robert de Koch, who's going to be telling us about scrambling in superangles. Also, I should assume you want to share your screen, actually, Robert, and I don't know if I have to.
I see. So what do I do from my side? So let me take a look at the Zoom. So let's see. Share screen, great. Very good. Share. So is it visible? I guess it's still.
Yeah, we can see it. If you can put it full screen, it's probably nicer.
Yeah. So it should be full screen now. Is it? Yeah.
Yeah, perfect.
Okay. So the work that I'm going to be talking about today is based on work that I did together with Eunice Gendote, a PhD student, and Lawe Mahu, who graduated a little while ago, and he is now faculty at the University of Ghana. So the basic question that I want to ask is, does n is equal to 4 Yang-Mills theory scramble information? Let's just discuss a little bit about what's involved. So as far as scrambling goes, most of the calculations that you will have seen for scrambling will have been done for something like a spin system, where the Hilbert space is a nice tensor product of individual Hilbert spaces for the spins. And then it's very easy to calculate things like how much entanglement there is, entanglement entropies, and things like that. And that's really the case where scrambling has been studied in the most detail. And it's because it's a very simple setup. So one of the things that we're going to have to face is how do you study scrambling in a field theory? And we'll see how to do that. The next thing, maybe just to mention, if anybody doesn't know what scrambling is, imagine I have an n particle system and I put some information into the system somehow. I mess around with one of the particles. We would say that that information has been scrambled when I basically have to measure the whole system to recover that information. This information is going to spread by entanglement, and it's essentially when the information that we put into that single particle has now spread to everything else in the system by entanglement. Now, if you believe ADS-CFT, well, then we would expect n is equal to 4 Yang-Mills as dual to quantum gravity on an ADS5 space-time. This would include things like black holes and all of the usual things that you expect from gravity. And then we would expect that, in fact, yes, Yang-Mills theory will scramble information. So that's at least what the common law would have us believe. But we'd really like to show that. And to show that, we're actually going to need to sort out some details. So what kinds of things are we going to have to get straight? So first of all, what operators should we be using? So we're going to want to study some operators. Exactly which one should we use? And what is the associated effect of Hamiltonian associated to these operators? So it'll be a familiar idea that the dilatation operator of the theory defines for you a Hamiltonian. And that's what we're going to do. We're going to take the one loop dilatation operator and see what dynamics we get from that. The other thing you'd like to know is this result generic. So if I give you a generic state with some generic perturbation, will it scramble? Does the system scramble or not? And then finally, one thing that might be worrying you is that we know the planar limit of n is equal to 4 Yang-Mills is integrable. When you've got a system that's integrable, there's a whole lot of extra conserved charges, and states with different values for these charges just don't mix. So your phase space breaks up into states that will not mix with each other. And you might wonder, will information really be scrambled or not if all of these different states can't talk to each other? So does the integrability of planar Yang-Mills prevent scrambling? And we'll have to answer that. So some quick questions. This is what I'm going to argue for during the talk. So what operators should be used? Certainly not single traces. So we're going to be studying operators built from order n squared fields. This is very different to the planar limit. And in particular, when you think about how operators mix, in the planar limit, different trace structures don't mix with each other. But away from the planar limits, in the limit that we're in here, for example, different multi-trace structures do mix. Because these operators are much more complicated, we're going to need a different way to label them. Usually in the planar limit, you label states by a spin chain state. Here, we're going to label multi-trace operators by a graph and a Young diagram. And I'll explain where those labels come from. If you then work out what's the Hamiltonian that you get from the one loop dilatation operator, it turns out that you get dynamics of a particle hopping on this graph. And I think that's kind of interesting because a lot of the models that were proposed as fast scramblers were things like Ising model on a random graph or something like that. And here we see a graph naturally appear from n is equal to 4 super-Young moles without us putting it in. And then is this result generic? Well, I'll give you some numerical evidence, not very strong numerical evidence, but some numerical evidence that it is indeed generic. And then finally, this last point is the easiest one to address. How does this mesh with well-tested tree-level integrability of n is equal to 4 super-Young moles? Well, integrability really is a property of the planar limit, and we're nowhere near the planar limit. So there's no integrability in this problem at all. Okay, good. So let's start off and talk about what operators should be used. Now, I want to give you a flavor of where they come from. I could make this very complicated. I just want to make it as simple as possible. So I'm not going to give you all of the details. But it's really three ingredients that determine the form of our operators. So the first one is that we've got gauge invariance. So what does that mean? That means all matrix indices must be contracted. So if I've got some multi-trace operator, as I've shown here, I can choose to represent it as follows. I can put all of the z fields next to each other. Let's say there's n z fields. These are some adjoints, some matrices. I've got some y fields. Let me put them next to each other, and some x fields, and I'll put them next to each other. And then which operator do I get depends on how I contract the lower indices with the upper indices. And one way of labeling how I'm going to contract the lower indices with the upper indices is with the permutation. The permutation that I'm talking about here will act on all of the fields appearing because I want to consider the most general possible contractions. So it's labeled by a permutation that belongs to the permutation group that permutes indices of all three types of fields. Now, if you label things like that, that's fine, but it turns out that for a given operator, there's more than one possible permutation you could use. And the reason for that is by permuting indices differently, sometimes the only thing that we've done is we've swapped two z fields around, or we've swapped two y fields around, or two x fields around. That must be a symmetry just by Bose statistics. So what we want to do is we want to divide out by a symmetry group. And this is a subgroup of the permutation group I've just been talking about. This group only swaps indices of z fields, y fields, or x fields. And it doesn't mix the different species. So that's why we've got these two permutation groups appearing. The first, so that we can get every possible operator, and the second, to divide out by redundancies. And there's another kind of redundancy that we need to be careful with. Let's imagine we've got a single matrix, and you're going to start calculating traces of that single matrix. So you can consider the trace of the matrix squared, the trace of the matrix cubed, and so on. After you get the trace of the matrix to the power of n, where we're talking about an n by n matrix, you've now listed all of the independent traces. So for example, the trace of the matrix to the power of n plus 1 can be expressed in terms of the first n traces that you have. And one way to see that, it follows because really this matrix only has n independent eigenvalues, and all of these traces can be expressed in terms of the eigenvalues. So we would like to write down a set of operators that is complete, but not overcomplete. And the way to do that, we use a nice piece of mathematics. We can Fourier transform from elements of the group to irreducible representations of the group. And there's a Fourier transform relating those two. And if I then deal with irreducible representations that have at most n rows, I have solved the constraints of finite n. So I'm going to be getting Young diagrams for both of the permutation groups that you see, and I'm going to be restricting to only n rows. The resulting operator is called a restricted Schur polynomial. The first label here, R, is a representation of the permutation group swapping all of the fields. And we've got 3 Young diagrams, R, S, and T. And that corresponds to a representation of the group that swaps only Z's, only Y's, or only X's. And then finally, when we're dividing out by this redundancy, there's more than one way to do it. These labels alpha and beta keep track of inequivalent ways to divide out by the redundancy. So we're dealing with a situation where the total number of fields is n squared. The large n limit is not the planar limit. It's much more complicated. We want to identify the effective Hamiltonian with the dilatation operator, and we can write it down exactly. The trouble is we can't diagonalize that Hamiltonian. It's just way too difficult. So the dynamics is too complicated to solve. So to make progress, we're going to try to simplify things a bit. So let me, before I describe the simplification, let me just introduce a little bit of physics. So when we look at this Young diagram, every row of the Young diagram will correspond to a giant graviton. So this is the D3 brane with spherical topology. The giant grows because of a competition of 2 forces. The tension of the membrane would like to shrink it to a point, but there's a Lorentz force because there's an RR flux in the ADS spacetime. And when this membrane moves in the background of this RR flux, the RR flux tries to puff the membrane out. We've got this competition between the Lorentz force trying to increase the size of the membrane and tension trying to decrease the size of the membrane. And the radius is set when these 2 forces exactly balance. Now, the number of boxes in each row of the Young diagram tells you what is the momentum of the corresponding giant graviton. And if you increase your momentum, well, then you increase the value of the Lorentz force, so the membrane is bigger. So longer rows correspond to bigger giant gravitons. Another fact that I want you to bear in mind, it'll make it easy to understand the form of the operators that we get, is just the Gauss law. So the Gauss law tells us the divergence of the electric field should be equal to the charge density. So if you want to get, so there's a typo here. If you want to get the total charge, this should be an integral of rho d3x. And then I just use the Gauss law to substitute for rho the divergence of E. And then I use the Gauss theorem to say this is an integral of E dot dA. But because I've got a spherical membrane, this membrane has no boundary. So this last integral is, there is no boundary, so it vanishes. So what this means is the total charge on any membrane has to vanish. So what are the takeaway points? Each row is a giant graviton, and the charge from any membrane the total charge on any membrane must vanish. Okay. So now I want to show you how we're going to simplify things. We're going to consider a situation where we've got many more Z's than X's and Y's. The Young diagram that you see, the big one, including the labels, that would be Young diagram R. That's the one that organizes all of the fields. The Young diagram that you see with none of the boxes written in it, so just drop the label boxes, that would be Young diagram little r, and that would be the Young diagram that organizes the Z's. The second Young diagram organizes the Y's. You can see there's a total of 6 Y's, there's 6 boxes here. And the last Young diagram organizes the X's. There are the 3 labels. The limit that we're going to consider that simplifies things is when these corners of the R Young diagram are well separated. And what I mean by that is the distance between this corner and this corner measured by the number of boxes that you have over here is of order n. The number of boxes between the second corner and the third corner is again order n. In that limit, it turns out there's a new symmetry. If you swap Y's and X's in the same row, it's a genuine symmetry, it leads to a conservation law. And in fact, when the dust settles, you can replace these operators by a new set of operators, these graphs, that make the symmetry manifest. So let me explain to you how they do that. If you think about any particular node in this graph, so there's 3 nodes, each node corresponds to a Young diagram. Each edge in the graph corresponds to a field, so either a Y field or an X field. If you swap 2 edges that land on the same vertex, that's obviously a symmetry of the graph. And that's how we built in the symmetry, the extra symmetry that we got. The extra conservation law that we got tells you that edges that stretch between distinct nodes do not transform. They're completely inert. But edges that are closed, so they just belong to a given vertex, they are in fact allowed to detach and travel to a different vertex. So what do we have here? The dynamics, so this you can derive just by looking at the dilatation operator. I didn't want to derive this because there's a lot of details. The dynamics follows from interpreting the dilatation operator as a Hamiltonian. If you've got a closed loop at a single vertex, it can detach and reconnect to a new vertex. And you can move to any vertex for which there are edges between the two nodes. If there's a vertex which is not connected to another vertex by nodes, you cannot move to it. So we're going to reinterpret this as a system of bosons. Each of these closed loops is going to be a boson, and it's going to be hopping on this directed graph. So there's bosons living at each of the p vertices.
I think she's good. Yeah, and I think
Jeff, your audio is on.
Okay, good. So the Fock space will be a tensor product of a Fock space for each vertex. And we've got these creation and annihilation operators that will create and destroy closed loops on the graph. And then it's the usual thing. Annihilation operators annihilate the vacuum, and the vacuum of the full Fock space is a tensor product of the vacuum for each vertex. We're going to introduce a p by p matrix, Nij. And what Nij does is it counts the number of edges between vertices I and j, and it doesn't bother about orientation. So these edges here have little arrows on them if you look very carefully. So they tell you there's some orientation. We ignore the orientation. So between 1 and 3, we have 3 edges. So these matrix elements in the first row, third column is 3, and third row, first column is 3, and so on. And in 2 and 3, there's 1 edge. Between 1 and 2, there's 1 edge. So that's why there are these 1s sitting here. And Nij has zeros down the diagonal. In terms of that matrix and these bosons, the Hamiltonian takes this form. The first term sitting here is just a constant, written in terms of Nij. Then we've got a term that looks like B dagger B, and another term that looks like B dagger B. So it's totally quadratic, very simple system to solve. The second term is an I dagger. So this doesn't move the loop around, but the third term will move the loop around. You destroy it at vertex I, and you recreate it at vertex j. The parameters that appear inside here are as follows. Li is the length of the row in the Young diagram that corresponds to vertex I in the graph. That's hit by the Young diagram. N plus Li is this parameter Ri. And what K is the total number of edges either ending on or leaving the vertex. Now, before I told you that the Gauss law tells you the total charge on the membrane must vanish. And what that corresponds to in terms of these graphs is that the total number of edges ending on the graph must equal to the total number of edges starting from the vertex. So for each vertex, same number of edges ending, and same number of edges starting from the vertex. And that embodies the Gauss law. Okay, so the first thing that I was curious about is counting these Gauss graphs. You see, the point is every single possible graph corresponds to a different state of the system. We're in the limit where we have order n squared edges in the graph. And what this is going to mean is we're in the right regime to be describing something like a black hole. Now we're at weak coupling. We're not using all of the fields of the theory. So this is probably just at best a toy model for a black hole. I wanted to count how many graphs there are to give me an idea of how many states there are. A black hole in this situation should have an entropy of order n squared. So the number of states should be something like e to something times n squared. So I wanted to see, can I reproduce that exponential and n squared growth for the number of states? Now, it turns out that it's easiest to talk about the oriented edges. So EIJ will tell you how many edges go from vertex I to vertex J. So EIJ from I to J. So this unoriented edge matrix is EIJ plus EJI. And again, the diagonal elements of EII vanish. Now, what do we need to impose on our graph? We need to impose the total number of edges ending on each vertex equals to the total number of edges starting from each vertex. And this is the middle equation that you see on the slide. So the sum over I of EIJ is the total number of edges ending on vertex J. On the other side, the sum over I EJI is the total number of edges starting from vertex J. So this is the constraint, the Gauss law constraint. The third equation on the page is just that the total number of edges is NE. So we might also want to impose that. So the set of matrices obeying the Gauss law constraint, I'm going to call curly E. And the set of matrices obeying the Gauss law constraint with NE edges, I'm going to call curly E NE. And what we would like to do for each matrix, there's a graph. So we want to count the number of matrices. So how do we do that? So let's try to set up some partition function that we'd like to calculate. So I'm going to define this operation F star E. And what F star E is, take Fij, so E and F are two P by P matrices. So I'm imagining that my graph has got P nodes in it. And F star E is just element Fij raised to the power of Eij. Don't put in the diagonal element, so I is not equal to j. And then just take a product over all of them. And then what I would like to do, I'd like to define this partition function d Gauss of f. So I'm going to sum over all matrices inside curly E. And I can refine the sum a bit if I like. I can sum over some positive integer ne, or non-negative integer ne, and I will sum matrices inside this curly E ne set. Now let's look at this last sum, the sum over E inside curly E ne. If I was to evaluate this at Fij is equal to z, then all of the exponents simply add, and I'll just get the sum over I and j of Eij, but that's just the total number of edges. Now it's very easy to do the sum, and you can see I'll get the number of graphs with p vertices and ne edges times by z to the ne. So if I was able to calculate this z Gauss and evaluate it at Fij is equal to z, expand it as a polynomial, and I'll figure out how many graphs there are. So that's what I'm going to try to do now. So how do we calculate z Gauss? So I don't know how to calculate z Gauss immediately, so let's do something simpler. So forget about this matrix dx for now, but look at zf. So zf is a sum over E, f star E. And this sum over E now is a sum over all matrices not being a constraint. So for example, the E1, 2 matrix element would be summed over 0, 1, 2, 3, going all the way up. Well, that's just a geometric sum for each matrix element. So the answer that you get from kind of high school mathematics is z of f is a product over I and j, I not equal to j, 1 over 1 minus Fij. That's just the usual geometric sum. Now what I'm going to do is I'm going to evaluate this partition function at dx minus 1, where dx is this diagonal matrix, times f times by dx. And if you take a look at dx, it's diagonal, so it's very easy to multiply it into the f, and you'll end up getting the expression shown. Now take a look at this exponent of xk. That exponent of xk is precisely what vanished when the Gauss law was obeyed. So in fact, the x independent piece of this z, which I just calculated, is the generating function for Gauss graphs, for the number of Gauss graphs. So how do I pick up the x independent piece? Well, I do the usual thing. I use Cauchy's theorem. So I'm just going to integrate over each of these x's, dx1 over x1 up to dxp over xp. I'm integrating them all over the unit circle, 1 over 2 pi I to the p. And this thing will now tell me how many Gauss graphs there are if I expand it out as a polynomial in Z. So here's just an example. Here's P is 4. So you can go ahead and calculate it. And this is the answer. So for example, what it tells you is if you've got 4 vertices and 15 edges, there's a total of 9,528 Gauss graphs that you can define. And we wrote a code in Mathematica just to actually write down all of the Gauss graphs, and well, it agrees perfectly with this number. Here's some table that I produced. There's just a few things that I wanted to show you. So the first 2 columns, well, the second and third column are for 4 vertices. The 5th and 6th columns are for 5 vertices, and the last 2 columns are for 6 vertices. If you're studying graphs with 6 vertices and 15 edges, you can see that there's already 24,983,264 graphs. So the number of graphs grows extremely rapidly. And what this suggests is we should be trying some sort of a statistical approach to study this problem. The other thing I think that is interesting is, let's look at the second and third columns. When we've got 2 edges, there's 6 graphs and none of them are connected. By the time you get to 15 edges, there's 9,528 graphs and 9,216 of them are connected. So you would have a 97% chance that your graph is connected if you just select it from this set. And in fact, we're going to see more and more as the number of edges grows, there are certain typical properties that you can expect from each graph. So what we're going to try to do is we're going to try to characterize what does the typical graph look like, because if you can write down what the typical graph looks like, then you know what the typical Hamiltonian is. And because the Hamiltonian just depended on the graph. And when you've got the typical Hamiltonian, you can ask, does that typical Hamiltonian scramble information? Does that typical Hamiltonian lead to dynamics which equilibrates? So that's the logic. But before we get there, let's do some asymptotic counting. Let's do a saddle point analysis to figure out what is the number of graphs when n gets really, really big. So here's our Z Gauss again. All I've done is I've said xi equal to e to the I theta I. So I've changed the theta variable. And one of the theta integrals I can do trivially because things only depend on actually differences in theta coordinates. So that's easy to do. In terms of this function L, you can write down the number of Gauss graphs in the form shown on the bottom of the slide. And it's this integral that I want to do by saddle point methods. So I'm going to figure out where the saddle point is in the thetas, where the saddle point is in Z, and just estimate what does this number of graphs look like for very large n. It turns out the saddle is at theta 2 is equal to theta 3 is equal to dot 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 is equal to theta p is equal to 0. So all the thetas are 0. And Z is number of edges plus 1 over number of vertices squared minus number of vertices plus number of edges plus 1. So if we now let the number of nodes in the graph scale like some small number times n, and we let the number of edges scale like a small number squared times n squared, then this is the number of graphs we find at large n. Now, the reason why I am asking that p scales like a small number times n, and why ne scales like a small number squared times n squared, is because I have to keep my displaced corners approximation being valid. The number of z fields is n, and that needs to be much larger than the other types of fields that I've got. So the number of edges and nodes in the graph must still be very much less than n. Sorry, I should have said the number of z field scales like n squared. So I need the number of nodes and edges to be very much less than n squared. And what you find is the number of graphs grows exactly like e to the 2 epsilon squared log 2 times n squared. So in fact, there are enough states in this Hilbert space to be able to describe the entropy of a black hole if we were able to work with strong coupling and include more fields. I think that looks promising.
Robert, can I ask a quick question?
Sure.
I might have just missed it at the beginning, but what was the reason that you needed to have more Z fields than X and Y?
Okay, so in general, you wouldn't want to do that. In general, you'd like to have the same number of all types of fields. In actual fact, I don't know how to solve that problem. The only problem I know how to solve is the one where you've got lots of Z's and much fewer of the other types of fields. Now,
And is that,
sorry?
Sorry, is that just because it introduces that extra symmetry that you were talking about?
Okay, so the extra symmetry is because the corners are well separated. So maybe I'd have some smart way of making sure the corners are well separated when I've got the same number of z's, y's, and x's. That may well be possible. Let me tell you why having a lot of z's really simplifies the problem. If you've got a lot of z's, a huge number of z's, then you're close to an operator which has only z's. But an operator which has only z's is a half BPS operator. So in actual fact, the same way that, for example, the BMN loops relax supersymmetry in sort of a systematic way by introducing a few fields with very many z's, I'm doing the same thing here. So you can think that I'm still pretty close to a supersymmetric state. So I still expect there to be lots of simplifications. So I think, so I could make this more precise, I guess, if we thought about it. We haven't done it, but we're close to a supersymmetric state, and that's why it makes it simpler. Okay, so now let's talk about the typical graph. So what do we mean by typicality? So we all know, if it happens in the vast majority of cases, the typical lottery ticket loses. If you flip a coin 1,000 times and you divide the number of heads by the number of tails, that's close to 1. These are what we mean by typical. How are we going to get a definition of typical for our typical graph? Well, you need to pick an attribute. So for us, it might be, is the graph connected or not? It might be, what's the number of edges at a given vertex? Something like that. And we need a probability measure, which I call mu p. We'll define this probability measure just by counting. So I'll generate the complete set of graphs. I'll count the total number of graphs, and then I'll count the number of graphs that have property p. And I'll divide the number of graphs with property p by the total number of graphs, and that'll give me mu p. If mu p tends to 1, as I keep increasing n, then I will say that p is a property of the typical graph. So that's how I'm defining typicality. Just wanted to make a clear statement. For us, when p is order epsilon n, and we've got p squared edges, the typical graph is connected. So that means, in fact, that's nice. Information can get scrambled all over the graph because you can travel everywhere. And secondly, the typical graph has p edges ending on or leaving each node. So roughly, everything is connected to everything, and the edges don't pile up anyway. They're kind of evenly distributed throughout the graph. And this is enough to say what is the typical Nij, because that's just telling us how many edges go between vertices I and j. In fact, the typical Nij will just be 1. Every vertex connects to every other vertex. And once you've got Nij for the typical graph, you know the typical Hamiltonian. Okay, so now let's talk about scrambling on these typical graphs. So basically, when you're asking about scrambling, you're asking how quickly is entanglement generated by the typical graph Hamiltonian. So that's one way to couch the problem. Now, in a situation like this, you might worry. So what's the nice thing about a spin system? A spin system has a finite dimensional Hilbert space. That means you're working with matrices, and you don't have to bother with functional analysis. You can just use linear algebra. And most of the results that have been established rigorously work for finite dimensional Hilbert spaces, not infinite dimensional Hilbert spaces. But here we have some luck on our side. You remember that the Hamiltonian was the form of B dagger B. And that means that it conserves the total number of particles. So it's absolutely consistent to restrict the dynamics to a subspace of Fock space with a definite number of bosons. And if you do that, you're back in the world of a finite dimensional Hilbert space, maybe very big, but still finite dimensional. And you can again do linear algebra, and you don't have to worry with functional analysis. So that's the first nice feature. And what we're actually going to do is we're going to try to calculate what's the growth of operators. So what's the idea here? So it's really the following. If you have an operator at early time and you have another distant operator, they will commute with each other. As you time evolve the system, so the operator at time t will get more and more complicated, and there's a time at which it will fail to commute with distant operators. And what we say is this operator is becoming a very complicated linear combination of all sorts of possible operators that you can define on the Hilbert space. And that's the size of the operator, you know. How many operators do you have to take in a product to produce this operator OI? It's very nicely defined for a spin system. So what we're going to do is we're going to study this commutator OI of naught. So OI is located at the ith Fock space. You can think this is an operator that acts only on the bosons at the ith vertex of the graph. And we're going to calculate a commutator of that with OJ of t, which is an operator which acts only on the bosons located at the jth vertex of the graph. And for early times, of course, this will commute, but for late times it won't. And we want to bound for how long does this stay small. And to obtain the bound, we're going to use kind of the usual logic of the Lieb Robinson bound. And in fact, it works very nicely in this setting. So I'm going to move from the B and the B dagger to an alpha and a beta I, which is fine. Alpha and beta are both Hermitian. That's what's nice about them. Written in terms of the alpha and the beta, H is a constant piece, plus half alpha I mij alpha j, plus 1/2 beta I mij beta j. And if you look at mij, there it is. So this nij appears, which we know what it is for the typical graph. Then we've got parameters related to length of rows in the Young diagram, n plus length of rows in the Young diagram. And if you remember, this number ki was the number of edges starting or leaving at vertex I. And again, for the typical graph, we have an idea of what that is. Because this is such a simple system, we can solve the Heisenberg equations of motion exactly. So we can work out what alpha k is as a function of t and what beta k is as a function of t, and we can calculate these commutators. So that's exactly what the commutators look like. So now let's start inputting some information about the typical graph. So let's look at off-diagonal elements of mij. So I've written what it is over there. Now the nij for the typical graph is 1. So we expect that this matrix element, we can just drop the nij. And then I'm going to write things in terms of p. And if you remember, p was equal to epsilon n. So I can smuggle the epsilon n downstairs. I need to put an epsilon n upstairs, which will turn the G angle squared into a Toft coupling. And then what I get is I get epsilon times lambda Cij over p, where I've defined what Cij is. Cij is very much less than 1, both because I'm doing weak coupling. I'm only looking at one loop, so lambda is small, and because epsilon is small. So these off-diagonal elements of mij are a small number divided by something which is growing like n. So they're very small. Of course, there's lots of them because we have to sum over n, but they're very small. For the diagonal elements of mij, we can again estimate what they are using a very similar kind of an argument. Just we know what the typical graph is, so we can say what these are. And these look like epsilon lambda times by ci. So mij looks like lambda Cij over p. So if I look at the magnitude of this matrix element, I'm going to bound it by some number c lambda epsilon over p. And this c is chosen to be bigger than all of the ci's and all of the cij's. It'll be some order 1 number, but just bigger than the ci and the cij's. That's how we could bound m itself. Now take a look at m squared. So the first thing I'm going to do is just write out what is this matrix multiplication. So I've just written out what the matrix multiplication is. The first term involves only off-diagonal terms. The second term in the absolute value is when I've got a diagonal term times an off-diagonal, or an off-diagonal times a diagonal. And then what I'm saying is the magnitude of the sum is going to be less than or equal to the sum of the magnitudes. That's true. And then for each of these terms over here, they're all going to be less than if I replace the CIKs by this number C, which was chosen to be bigger than all of the CIKs. So what you see is m squared is going to be less than 3c squared epsilon squared lambda squared over p. And in fact, a very similar argument just tells you that m to the n is less than 2n minus 1 times c to the n epsilon to the n lambda to the n over p. So now what we can do is we can take the answer for the commutators, we can expand it out, take the magnitude of both sides, use the fact that the magnitude of the sum is always less than the sum of the magnitudes, and we know how to bound each term. And what you get from doing that exercise is that the commutator is less than this Koch plus this inch. So we've bounded the growth to be less than exponential. And this is typically the kind of a form that you get from a Lieb Robinson bound. Now, if you want to scramble with something, you must be entangled with it. And if you want to entangle something, you must be able to signal to it. So before we can become scrambled, we need this commutator to be greater than delta. And this time t sig is the signaling time. It's how long it'll take you to signal to that other vertex. So it's the amount of time you need to signal from J to K. The signal doesn't propagate instantaneously, it'll take some time. What you learn is using the Lieb Robinson bound, so this exponential growth, is that the signaling time must be greater than log P over epsilon lambda C. This is nicely consistent with the fast scrambling conjecture. The fast scrambling conjecture tells us that you cannot signal in a time faster than log of the number of degrees of freedom, which here is measured by P. Okay. So now let's talk about whether this typical graph system equilibrates or not. And the classical idea of equilibration is not very useful. We're meant to evolve towards thermal equilibrium. That you can't do if you're a quantum system. And that's because if you have unitary time evolution, you know that you're going to have recurrences, and you know that you've got time reversal invariant dynamics. So the system can never come to equilibrium in the classical sense. The best you can do, well, there's two notions that people usually use. So the first one is equilibration on average. So you've got some time dependent observable, and we say if it has it's equilibrated to some value, if on average, most of the time it's close to some value. So that's one notion that people use. Another notion, which is actually what we're going to use, is equilibration during intervals. The time-dependent property equilibrates during a time interval if its value is close to some equilibrium value for all times in that interval. So you start off at some state, you come close to some value, then you stay close to it for a long time, but then the system has some recurrence, you go away from it, but then you come back to the equilibrium value. And that's the best notion that you can get of coming to equilibrium in a quantum system. So we're going to use equilibration during intervals. And the reason why we're going to do that is that this is going to give us some idea of the time it takes to come to equilibrium. And that's specifically what we're interested in. Okay, so how do we tell, or how do we show that the system has come to equilibrium? Well, first of all, we need to know something about what is the equilibrium state. The equilibrium state is going to be the one that maximizes the entropy, just given by minus trace rho log rho. And it's been proved that the state that maximizes the entropy for a given mean in second moments is the Gaussian state. So how would the mean and the second moment be defined? So we take some B of alpha. This would be a sum over creation and annihilation operators with some complex coefficient. The mean would be the expectation value of B, and the second moment would be an expectation value of B times B. Okay. Now, usually in these equilibration arguments, it's nicer not to discuss the density operator, but rather the characteristic function. And that's good enough. The density matrix characterizes the state of the system, but the characteristic function does too. And there's theorems showing that you can reproduce the density matrix given the characteristic function. So what is the characteristic function? It's given by the expectation value of these while operators. So you exponentiate B dagger and B with some complex coefficients, beta I. And then what is a Gaussian density matrix? The Gaussian density matrix is a characteristic function that is the form given. So what we're going to do is we're going to start off in some arbitrary state. We're going to ask ourselves, at long time, do we approach a state such that the expectation value of the characteristic function has the form shown? And then the system has come to equilibrium. And how long do we take to get to that characteristic function? Good. Sorry, there's a typo here as well. This should be trace rho d of beta. Okay. So the reduced density matrix is defined as usual. So we just take a trace over everything that we call the environment of the state phi phi. And we're going to trace over everything except for vertex I. So the environment is going to be everything except for vertex I. What is the state that we're starting in? We're going to stick m bosons at every single vertex. So this is nothing like the equilibrium state. At equilibrium, we expect a very entangled state. This is in fact a tensor product, so there's no entanglement at all. And we're going to calculate what is this characteristic function equal to. Well, this is a relatively simple calculation. People in quantum optics do it all the time. And it's given by a product from j is equal to 1 up to p of some Laguerre polynomial multiplied by this exponential. And you can see there's a uij appearing. The way that the uij is defined is that bi of t is just given by uij acting on bj. Okay, so what would we like? We would like it if this characteristic function becomes this exponential of the alpha squared. So you can see what we really need is for the Laguerre polynomial to become 1. But if you perform a small x expansion for the Laguerre polynomial, you can see that it does become 1 plus some corrections. So what we would like to know is, does the argument of the Laguerre polynomial become very small? So does mod alpha squared times the mod of uij squared become very small? And in fact, if you take the typical Hamiltonian, you can calculate uij, and it gives you a Bessel function. This quantity v here is defined as follows. So I'm taking vi to be 2 lambda epsilon over 4 pi squared ri over li. And to simplify the calculation, I'm assuming that these vi's are all roughly the same. So vi would be approximately equal to vj for any I and j. So it's again another restriction on how general this is, but for this case, we can actually solve it. And then we use the fact that the Bessel function is always less than x to the minus 1/3 for all x greater than or equal to 0. So for large times x, which is this condition over here, we know that we're going to get a Gaussian density matrix. So indeed, the system does equilibrate, and it equilibrates in this time. T equilibrium is p over 2v squared. So the time that it takes the system to equilibrate scales with n. The time it takes to scramble is about log n. And the current time would be exponential, double exponential in p. So the system scrambles pretty quickly, then it equilibrates, and then it spends an enormous amount of time in this equilibrium state, and it will come out of it at the recurrence time. Okay, so I'm going to finish off now. So let me just mention a few future directions. So it would be great to be able to extend this beyond weak coupling, but that's really a bit of a dream. I don't think anybody knows how to go beyond weak coupling. So for now, we're stuck with weak coupling. We would like to involve more fields. That would be pretty easy. That wouldn't be hard to do at all. But I think that you might be able to now start looking for things that had quantum numbers that resembled an actual black hole that we've studied in ADS. It would also be nice to evaluate the OTOC and see what does it look like, and to move beyond distant corners approximation. Now, moving beyond distant corners approximation is perhaps the most interesting thing to do. It's still doable, but it's hard. If you move beyond distant corners, you pick up terms that are quadratic in the B's in your Hamiltonian. And what that means is graphs of different shapes can start to mix. At that point, all of the states in the Hilbert space will start to mix. And I think we can be reasonably sure that you would expect chaos. I think it would be very nice to calculate the OTOC beyond the distant corners approximation and to see what the Lyapunov exponent looks like. It is still weak coupling, but it might be interesting to see, does it at least have some features that you might expect for a system that's going to develop maximal chaos? I don't know. And thanks for your attention.
Thank you very much, Robert. Very interesting talk. Does anyone have any questions?
So I have a quick question, Robert. So can you, I know you in your future direction, you mentioned about what you see, but can you quickly see the unequal time commutator square? Because you already computed the unequal time commutator, right?
Yeah, that is true. So let's see. So Shajid, for this system, so let's see, good. So here was the commutator.
Because that will give you a sense, right, for auto.
That's a good point, absolutely. So here they are in equation 4.
Yeah, exactly. So this is, yeah. You had a slide with alpha t and alpha 0, right?
Let's see. You mean this one?
Yeah, exactly. But this is this beta is the alpha at 0, right? T equals.
That's correct. Yep.
So this is this is your just the commutator, right? So if you square it, right? So it's, you get a combination of Gaussian sinh squares. So I guess
that's still exponential.
Right. There is some. I'm pretty sure at certain t there will be some exponential limit, right? I mean, for a certain.
Yeah.
So I think you can guess it already from here, roughly.
I would imagine so. You know, Shajid, I'll tell you why I did this calculation here. I'll tell you what disappointed me. So that exponential growth should be telling you something about the Lyapunov exponent, right?
Right. Exactly. Yeah.
Now, if you really have a chaotic system, you would expect the spectrum to show Wigner-Dyson statistics.
Yeah.
Now, Wigner-Dyson, you should expect if the system is ergodic, so the whole phase space mixes.
Okay. Yeah.
And here, each graph of a different shape doesn't mix with other graphs. So there might be some weak chaos in each sector, but I don't think this is anything related to what you would expect really for a black hole. I think for the black hole, you need the corners on the Young diagram to be close. I think that different graphs are going to start mixing, and all of the states in the Hilbert space are just going to be mixing without any constraint at all. So in that case, I really think that there is complete ergodicity, and I'd expect Wigner-Dyson statistics.
So maybe slightly unrelated. So when you write down the Hamiltonian, right, there are a bunch of sums. So can you treat them like separately, or do you have to do really the sum? Like, is this?
So let's see, here's the Hamiltonian.
So yeah, exactly. So these sums, right, here. Yeah. Can you go by like a term by term, mode by mode, or?
You know, well, so this would be a diagonal mode. So this is telling you there's some energy for sitting at a particular site. Yeah. Costs you something to sit somewhere. And you actually gain some energy. You lower your energy by moving around. So actually, what this state would like to be, the boson doesn't like to be located somewhere. It likes to be spread out across the graph. That's what this is doing.
Yeah, okay.
Sorry, I have a question.
Yep.
So you said when you deviate from the separated corners approximation, you will pick up terms in the Hamiltonian that would look like b squared. Is that right?
So things that look like b dagger.
Okay, so you're picking up things that are quadratic and sorry, that are
quartic
in the B's.
Yep.
And the expectation there is that you would see chaos in that approximation because you're getting mixing of graphs.
Exactly. So all of the states in the Hilbert space mix nicely.
Mm-hmm.
When you've got the distant corners, you've got this extra symmetry. And that extra symmetry prevents graphs of different structure, different shapes from mixing. That's the conservation law associated to it. So that limit of the theory has extra conservation laws, which usually is not good for chaos.
That's right. That's right.
but it's hard to calculate those terms. So I tried it on South African students and struggled. Now I've got a Chinese student and he's still going, so let's see.
Is that just a statement about his stamina versus South African students? Or?
He's got extreme stamina, in fact.
Okay.
Excellent.
We'll see if we get something out.
Can you say anything about the spectral form factor with these graphs?
That's another cool question. I would like to calculate the spectral form factor for this. I think that's an interesting thing to calculate.
I mean, the one thing is because of your additional symmetry, unfolding of the spectrum will be a bit complicated there.
Well, you would restrict yourself to one subspace and you would unfold inside that subspace.
That's what I'm saying. So unfolding the spectrum would be a bit complicated, but restricted to specific subspaces, especially if those subspaces are closed and your graphs are not mixing.
Exactly.
Should be a little bit easier numerically, at least, right?
Yeah. So you would take this Hamiltonian with a fixed Nij.
That's right.
Study its spectrum.
Yeah.
Mm.
I mean, with the fixed Nij, right? You can perhaps also look into computing complexity as well. I mean, very similar Hamiltonian, right? I mean, it just. I mean, up to certain simplifications, I think it's possible, probably doable, at least numerically. I mean, you can.
Oh, that's interesting, Sajid. So I don't know much about complexity. I would like to learn more. So this is the kind of a Hamiltonian for which you could calculate that?
Well, I mean, not exactly, but you can perhaps make some simplifications, right? And then you can do, at least for, you can do a series of oscillators, right? So like a sum of oscillators. So it looks very similar to that, right? Roughly speaking. So if we can do the sum of oscillators, then you can, at least numerically, even in Mathematica, you can do those computations for complexity. So perhaps this can be done as well. And complexity can, you can read some Scrambling information and perhaps Lyapunov, all these things from complexity as well. That could be one or two.
Yeah, very interesting. You see, what I find interesting about this system is it is dynamics on a graph, which has kind of been natural systems to study various many-body physics effects. But now this is coming directly from n is equal to 4 to P moles, which I think is kind of interesting.
Yeah, yeah. Mm-hmm.
And usually with the gauge theory, you can't easily find situations where you have a nice tensor product of the Hilbert space, and you can just do knowledge that you knew from spin systems. So,
yeah, this Hamiltonian is very encouraging, I would say.
Yeah, very simple.
So, Robert, I have a question. So that motivation aside, I mean, that's really nice that it appears in the Yang-Mills problem. But suppose I start off with this Hamiltonian, this red Hamiltonian here, and I replace the bosons with fermions.
Yeah.
What do you expect would change? The reason I ask is because, if you take away the physics in the problem and you just go to the graph theory, you have interactions and you have nodes, and really what matters is your adjacency matrix there. The graph doesn't really care too much about, the network theory problem doesn't really care too much about what's sitting at the nodes. What would you expect would change if I do that?
So interesting question. So I haven't looked at the fermions at all. I guess what would be nice is there you really do have a nice finite dimensional Hilbert space.
Exactly.
Yeah. But by the way, the problem with the fermions is also n is equal to 4 super n moles, because the limit in which we derived this one loop Hamiltonian was in the SU23 sector. So there are actually types of fermions. So there are closed loops corresponding to fermions. And what you can prove is inside the state space is that graphs vanish as soon as you have two loops of the same type at the same node. And that's just the Pauli exclusion principle.
Yeah.
You're also allowed to have two identical fermionic edges going between two vertices.
Yeah.
If you were to redo this calculation, replacing the x fields by fermions, you would get almost exactly the same Hamiltonian. I mean, I need to check it, but you then get a Hamiltonian for fermions hopping on a graph, and it's also
Fermions would be Dirac.
fermions.
Yeah.
Well, these came from Weil fermions in 3+1 dimensions. But here
Okay.
it would some. I mean, it would in a sense. If you mean are they complex, they would be complex.
That's what I mean. Yeah.
Yeah, they would be complex.
Okay. Okay. That would be very interesting.
Cool. Well, if there are no more questions for Robert, just thank him one more time for the very nice talk. I will
Thanks, Robert.
end the
Oh.
meeting.
Thanks.
Stop.